Okay, go for it.
Okay, so with regards to the oxidation of alkenes, I have about, I think only three, but rules that I have, I just wanted to make sure that they're fine. So if you have a carbon double bonded to another carbon, and then now you oxidize it, will the double bond break? And then you'll form one carbon will have a double bond to an oxygen, and the other carbon will have another double bond to an oxygen.
Correct, 100%. So that's first rule.
So, and if you have a carbon with an H2, and you oxidize it, will the H2 be then replaced by oxygen with a double bond?
100%.
So there will be a carbon double bonded to an oxygen.
Correct.
And the last one is if you have carbon bonded to a hydrogen, then you oxidize that, that becomes an OH group bonded to the carbon.
Correct. In other words, you would form the aldehyde, but because it's a strong oxidation, it would go straight towards carboxylic acid, which is the OH group. Correct, 100%. So you replace the H with an OH.
Cool. I think that's about
it. And then if you the last rule is if you have no hydrogens, you get the ketone, because then you don't get it at the end of the molecule, you get it somewhere in the middle of the molecule. So if it's bonded to two carbons, then you get the ketone. So you're absolutely correct. There's three scenarios. You're going to get carbon dioxide, the carboxylic acid, or the ketone, depending on what that carbon is bonded to.
Cool. Thanks, sir.
Cool, no worries. I'm going to see now if the iPad works. If it doesn't, I'll just keep using the screen. Just give a second. And then I want to quickly talk about the question you had yesterday, because it's also quite an important one. Let's see if the iPad works now. If it doesn't, then I'll just continue working on the computer. Here's the pencil. I lost the pencil now. Uh-oh. Pencil. Hello. Sorry, just give me a second. I'm looking for my pencil. I dropped it somewhere. I put it in a pocket, or I put it somewhere that I can't find it now. Oh, there it is. Ach, no, the iPad is not working in any case, so I'm gonna just do it on the computer today. It doesn't really matter, but I just want to quickly go over. Kamoz had a question yesterday. I'm going to share the whiteboard quickly, and then, if I remember correctly, the question was something to do with if you oxidize something, or if you add an OH group, do you get some kind of Markovnikov selection? Was that your question yesterday, Kamoz?
Yeah. Yes.
Okay, cool. So if you look, for example, at sorry, I need to share not the whiteboard. I need to share the PDF. Wrong PDF. I need to share part one. Okay, so when it comes to substitutions, when it comes to these ones over here, if you have the substitution to the halogen alkane, there's no preference. There's no it can't decide where it's going to go. So the carbon that it was on in the first place is the carbon that it's going to go on in the second molecule. So you'll see here that it's literally a 1-for-1 swap, and that one is going to go and replace that one. But in this case, it didn't really have a choice. There was no end carbon, no middle carbon, or anything like that. Ooh, but if you look at the next one, when there's a bigger molecule, so for example here, it's the same thing over here. The OH started over there, and it ended over there. It started over there, and it ended over there. It can't jump to the middle carbon to form the primary or the secondary in that case. But I don't think that was your question. Sorry, Kamoz.
I think that was, yeah.
I can't remember exactly where we started with this, because we were talking about OHs and whether we were going to form primary or secondary. I'm just trying to think in what context. In fact, you know what we need to do? We actually need to go back quite a bit, and we need to go back to alkenes. We need to go back to alkenes part 2, if I'm not mistaken. Nope, not part 2. We need to go alkenes part 1 over here. There we go. Okay, so here's a good example. So this, I think, is important. So here, for example, if we added the water to the double bond, so we add water to the double bond, you can see here that the secondary carbon is formed. So the secondary alcohol in this case is formed. This is secondary alcohol. That's a secondary alcohol. But you could also get the primary alcohol. And in this case, it's Markovnikov selection. In this case, it is a matter of it's going to prefer to be the secondary alcohol than to be the primary alcohol. I think that maybe answers your question a bit better.
Yeah.
Yeah. So if you look at this, no, there was no other example. In this case here, you could have potentially got the other product. You could have also got the, I'm going to see if I can just cheat here and write the O over there and just scratch that out over there. So that's the easiest way for me to do that. And that would be a primary alcohol. Also, this over here would be a primary alcohol. Yeah.
Would you say that that would be a minor product because
exactly.
OH is on a carbon with more hydrogens?
Exactly. So if I understood you correctly, maybe the confusion was when you do these kinds of addition reactions, you would almost always prefer to form a secondary alcohol than to form a primary alcohol.
Yeah.
But what it doesn't mean to say is it doesn't mean to say that primary alcohols don't exist, because they exist on their own. Like, for example, this here is a primary alcohol which exists, and it's very happy being a primary alcohol. It has no issue with it. Cool. And then if you go back to, I think the last one, if we go back to halogenoalkanes, I think this is where we're going to find the question. If you do a substitution, if you do a substitution, you don't have a choice to form the primary or the secondary. So in this case, the bromine was on a primary carbon and the OH gets formed on a primary carbon. It doesn't have a choice to form on a secondary carbon. So in other words, the substitution takes place where it has to. It doesn't have a choice to move to a different carbon. There's no good example of that.
So the textbook, they also talk about like nucleophiles and electrophiles. Do we need to know those things?
We do. We'll talk about nucleophiles and electrophiles when we do the mechanisms. So we'll talk about the mechanisms of these things.
So we're going to come back to the mechanism stuff.
Correct. So if you just to quickly give you a reminder, I know we've been doing this almost 3 weeks now, but just to quickly remind you, if you go to, no, not this one. Trying to think which is the first one. No, I can't remember now which is the first. But in any case, if you go back to the first lesson, we broke it down into 4 things. We said functional group conversions, we said testing, and we said mechanisms. So we're going to do all 3 of those separately. I can't remember which note it's on right now, but it's there somewhere. Cool. So for today's topic, I just want to quickly talk about the difference between strong oxidation versus mild oxidation. And it's in alcohols part 2. So it's this note over here. And you'll see here that we mention mild oxidation and strong oxidation of primary alcohols. Also, the only difference between the mild and the strong is that if you do the mild oxidation, you get the aldehyde. If you do the strong oxidation, you get the carboxylic acid. I'm just trying to think now. I haven't used the computer in such a while. I'm so used to the iPad. If you go forward and you have a look here we go. So have a look at this one. The mild oxidation, we're going to use what's called distillation. So distillation literally means that once the product is formed, it gets distilled off. So if you look at a distillation apparatus, it says that the product that it forms is going to be evaporated. And once it's evaporated, it comes out of the container. So if you just think of good old fashioned, if you just think of this, I'm going to show you the screen now. If you think of this kind of apparatus over here on the right-hand side, this would be what we would call like a distillation apparatus. Cool. So can everyone see that on the screen there at the moment? The distillation apparatus, can you see that on the browser?
Yes, sir.
Yeah. Oh, sorry. I didn't see the thumbs up. I've got that covered. Okay. So here where 15 is, this over here, you would put your alcohol. So you would put your primary alcohol here. So you would put the prime alcohol here with the oxidizing agent. Also, the oxidizing agent that we generally use is the potassium dichromate because it's a very good oxidizing agent. And then what will happen is that the aldehyde will form. and the aldehyde has a lower boiling point than the alcohol, so it's going to evaporate. So the aldehyde that's going to form is going to go up the tube, up the tube, up the tube, and then it's going to come down the tube, down the tube, down the tube. And then here at number 8, we're going to collect the aldehyde. Also, we can get the aldehyde straight out. Also, if we use distillation, it's a very mild process because the aldehyde that is formed evaporates and we can collect it as the distillate. So we can remove it almost instantaneously. Cool, everyone happy with that? I can't see thumbs up, so just shout quickly.
Yep.
You good?
Yes.
Yeah, and that's what we mean by distillation. So mild oxidation involves distillation, and the reason is because we can remove the product as soon as it's formed. Cool, and then they want you to contrast that to reflux. And reflux looks, not gastrointestinal reflux, chemistry reflux. There we go. And in a chemistry reflux, you would do something like this. Cool, so you would do something like this. And in this case over here, if I draw on the screen, do you see it? So if I draw that, do you see that?
Yeah.
Oh, good. Okay,
Yes,
good.
sir.
Yeah, so all your reactants over here. So you put your primary alcohol over here. So your prime alk and your oxidizing agent all go down in this container over here. And then it's heated. And then what happens to the aldehyde is that it starts evaporating. It evaporates, it evaporates, it evaporates. But because it's in this cooling tower, it's literally going to evaporate and fall back down again. So it falls back into the mixture. So it evaporates, it becomes the aldehyde, and the aldehyde kind of comes off for a brief moment, but then it gets condensed back into liquid and it literally drips back into it. So what you find is that at the bottom of here, what you get inside the container is now you have the aldehyde. Also, you have the aldehyde that is now in the container, and it's still mixed with the oxidizing agent. And this is why you get the further oxidation, and this is why you end up with the carboxylic acid. Also, if you go back to the conversions, if you do a primary alcohol with mild oxidation, primary oxidation, you're going to get the aldehyde. Well, and the reason is because the product is going to come out and you can take it away from the reaction mixture. But if you leave it in there for longer, if you let it reflux, if you let it drip back into the mixture, that's what this means over here, strong oxidation under reflux, you're going to form the carboxylic acid. Well, and remember that aldehydes and carboxylic acids always have to be at the end of a carbon chain, and so do primary alcohols. So you can see the link there between primary alcohols either becoming aldehydes or primary alcohols becoming carboxylic acids at the end of a molecule. Just want to quickly see. Thumbs up, everyone happy with that? Yep, you're good. Good. So that's the difference between strong and mild oxidation. And then if you have a look at the ketones, sorry, not the ketones, sorry, the secondary alcohols. Secondary alcohols don't have a choice to form an aldehyde or a carboxylic acid because they're in the middle of a molecule. So whether you do mild or whether you do strong distillation or oxidation, you're always going to go from secondary to ketone. Cool. So secondary to ketone, and you can do it mild or strong, it won't make a difference. It can't get further oxidized. So if you look at this carbon, I'm going to just circle it for you quickly. If you look at this carbon over here, we can't add more OHs and stuff. So we can't add, like, for example, another OH there because carbon can only have 4 bonds. So the only way we could do that is if we, for example, broke a bond over there, and in which case we're going to break the molecule and get different products. But that's not what happens. Cool, so a ketone is as fully oxidized as it can possibly be. You can't oxidize it further. Cool, and then if you look at, I'm just going to draw this as an example. If I draw a tertiary alcohol, so if I draw a carbon with a carbon, with a carbon, I'm not going to draw the hydrogens to make it a bit easier. This would be a tertiary alcohol. Just quickly, somebody tell me, why could you not further oxidize a tertiary alcohol? So why can't you change it? Why can't you turn it into something different? So who can think about why it's not possible to oxidize a tertiary alcohol? Ooh, anybody? Gloria? Kamaz? I think we might have internet connections. No. Anybody? Gloria? Stefan? Why do you think it's not possible to further oxidize a tertiary alcohol?
Because there are like 3 carbons already attached.
There's already 3 carbons attached. So how many bonds can carbon only form? What's the maximum number of bonds?
4.
Correct. And if you take the OH group, you can't now take this and form a double bond over there, because then carbon's going to have 5 bonds. So if you look over here, we already have 4 bonds. And if you have a look over here, this is 5 bonds. And I'm just going to go down to the bottle and say not possible. So it's not possible to form carbon with 5 bonds. You can't have a ketone that's bonded to a carbon that's already bonded to 3 other carbons. So tertiary alcohols cannot be further oxidized. We can't convert them into ketones or aldehydes. Cool. Any questions there? Should I go over that again? Yep, you good? So tertiary alcohols, no conversion. We can probably do a substitution, or we can do something else, but we cannot further oxidize them. Cool. As far as oxidation goes in terms of alcohols, that's basically all you need to know, is that you can take alcohols and you can make what we call carbonyls, or we can make carboxylic acids. So if you go back to your functional group, I'm trying to think if it's yeah, it's this one over here. We can now start having a look and seeing. Spotlight, does that work? What does that do? No, Spotlight doesn't do anything. Let's see which one's going to work nicely. This one over here. We can now go from alcohols to aldehydes, so we can do that path over there. And then we can also draw another path that's not in here, and we can say that we can go directly from alcohols to carboxylic acids. And then also what's not on this here is ketones. So you can say that we can also go to ketones, and you can add another little box over there somewhere. So can you see we've basically almost covered this entire grid? The only thing we haven't done yet is esters. Cool. So can everyone basically see we've covered almost the entire grid?
Yes, sir.
We're basically there. And then you'll see with the carbonyls, we can literally go backwards, and instead of doing an oxidation, we can do a reduction. So we can take the ketones and the aldehydes, and we can go backwards to form the alcohols. But that's for the next lesson. Cool. So I think if we're done now, let's take a 10-minute break and then come back at, let's say, 35 past for the next lesson.
Sir, can I quickly ask a question?
Of course, yes, you may. The rest of you, if you don't want to listen to the question, you can go. Otherwise, you can stay and have a listen to the question.
So a carbonyl is just carbon double bond with oxygen. So
100%.
are ketones and aldehydes like, can they like fall under the category of a carbonyl, and then you just further
Correct.
differentiate?
So can you see the screen that I put up now? The PDF?
Yes.
Yeah, this is literally the next topic. So yes, carbonyls are aldehydes and ketones. Absolutely.
Oh, okay. Cool.
Yeah. So when we say the word carbonyl, we just mean aldehydes and ketones. Carboxylic acids would be like a modified version of a carbonyl, but they're sort of separate functional group. We don't consider them carbonyls. Cool. So take a 10-15 minute break, and then we can do a quick 10-minute lesson just to go over carbonyls, and then we're done for today.
When should we come back? At like what time approximately?
Oh, I'd say 23, add 15. Let's make it 40.
Okay, 20 to 12.
Yeah.
Cool.
Oops, see you now. Bye.